And I'd like to welcome to the stage Dr. DK Panda and his colleague Bharath Ramesh, both from OHU. DK is professor and University Distinguished Scholar of Computer Science and Engineering at Ohio State University, who is in charge of the IMPACH 2 MPI libraries designed and developed by his research groups, which are used by more than 3,300 organizations worldwide. And Bharath is a graduate research associate in the Network-Based Computing Laboratory, working on IMPACH 2 library.
Okay. Can you hear me?
We can, DK.
Okay, good. So thanks, Phil, for the introduction. So myself and Bharath, both of us will be presenting. Bharath will be sharing the slides.
Yeah, can you hear me?
Yes.
Yeah.
You should be able to see my screen, right? Okay.
Yes.
Yes. Okay. So thank you. So this talk focuses on how to design in-network computing, our reduction collectives, especially in MPI. Next slide, please. So the outline will be as follows. We'll start with a very high-level introduction, followed by some background, motivation, problem statement, and the designs, and some of the performance numbers, and the conclusion. Next one, please. So as many of us know here, I mean, the modern days, like any HPC cluster we see, so there we see that these are the kind of the different drivers. What we see, like we have multi-core main-core processors, high-performance interconnects like InfiniBand, Rocky, even Slingshot, different kinds of accelerators, and NVMe, SSDs, and all are coming. And these are the ingredients of all the different top 500 computers we see, and also the cloud providers. Okay, so more or less like the similar kind of architectures are being provided on both kinds of systems. Next one, please. So in this context, I think this talk is focusing on especially the collectives. I think we heard several talks about these collectives and especially the MPI programming models. And what we'll be focusing here is the MPI all reduce. As many of you know, this MPI all reduce is very common in the traditional HPC applications. And there it has focused on like a short messages. So when we say short, like it could be like 8 bytes, 16 bytes, even up to 1 kilobytes, 2 kilobytes. And especially now with the new AI workload, especially with the large language models, we see this very similar kind of operations, MPI all reduce taking place, but very large messages. It could be megabytes or could be gigabytes. Of course, the MPI libraries, people have been designing all reduce collectives for many years based on the architecture. One can have very purely CPU-driven collectives or even GPU-driven collectives. But here, what we'll be trying to focus on is that can we offload some of these things to the network, especially the network switches? And then if the network switch has that kind of a capability for offloading some of the operations, how we can bring the capability from the CPU side as well as from the networking side and put a complete solution for the high performance implementation of all reduce, and then what will be the performance and scalability of that. Next slide. So move ahead. So this is where I think some of you know we started this work together with Mellanox, introduced this concept called SARP, which is like a scalable hierarchical aggregation and reduction protocol. So if you see on the left-hand side, so the idea is that you can always build this MPI all reduce on top of point-to-point communication, and gradually we'll go into more algorithms. The point-to-point communication can happen within the node or across the node. You can design hierarchical algorithms. But then as the messages are passing through the network, the idea is that can the switch provide some additional logic? Okay, and that's what you see on the left-hand side, like an aggregation tree. So the red ones, if you see, the data is actually moving up depending on the topology. You can call topology, and let's say I'm trying to do an MPI all reduce. Everybody pushes their data, and then it goes on the tree. And then after it reaches the tree, it has been reduced, it can be broadcasted back. Okay, and then this the right-hand side is trying to show you can also do streaming aggregation, and especially trying to show an example of a switch level reduction with a radix 16. Okay, So that's what we'll be focusing on the SAR based things, and then see how to optimize it for small messages as well as for large messages. Next slide, please. So let's start with the small messages. As we know, like these days, all are like a commodity clusters. Every node we see, like within the node, we have multiple sockets. And then each socket has again multiple cores. So typically, you need to do this already used with multiple stages or phases here, we'll call it. So these are like a color coded here. You will see like we need to assign different kinds of shared memory. It could be a socket leader based shared memory or intra socket shared memory. And then some of the dotted lines are like a writing, and then the solid line is the reduction. So in the phase one, you can think of like a intra-socket reduction. So all the cores which are within the same socket, we can provide a buffer. That's like a gray buffer here, and then the reduction can actually happen there. Then in the phase two, now I need to do the inter-socket. So I have reduced within one socket, similar reduction has happened another socket. Then I need to define another the socket leader based shared memory where these data go, and then it can be reduced. Next slide, please. And so then the question is, now I need to do internode because I have reduced the data within the node, and this is where I need to move across the node depending on the network. And this is where we can actually try to use the SAR. Okay. So of course, the first two phases we'll do it internally. This phase three will go over the network. And then next slide, please. We need to do the reverse phases 4 and 5. So that means we have done the reduction. So now we need to do the completely reverse order in the inter-socket broadcast. That is like a phase 4, and then the phase 5 is the inter-socket broadcast. So after these 5 phases, we have actually done the MPI already used across all the cores. So now the question is, next slide, how do we see the performance? So these designs, we took it and then we incorporated into the MHAPIS project. Many of you in this community must be knowing about this project. We started this project almost day one of InfiniBand. In 2000, prior to that, we were working on like the prior generation networks like Mininet Quadrix, and one is InfiniBand came. We were the very first one in the world to have the high performance MPI library over InfiniBand. We demonstrated it at Supercomputing O2. And since then, I'm very proud of my team. We've been continuously working on this project for 23 years, and it's very widely used, as you can see here. And just from the website, OISU website, we crossed 1.77 million downloads. And of course, it is available in a lot of other software stacks like Red Hat, SUSE, OpenHPC, SPAC, and our stack is deployed on a lot of top 500 clusters. Now let's look at some of the performance numbers. Next slide, please. So these were taken on TAG Stampede. As you know, the Texas Advanced Computing Center, the system is Frontera. The Frontera is the largest one. Here you can see like 7,861 nodes. And we took these small messages, as you can see on the x-axis, 4 bytes to 1 kilobytes. And we have the MHAPIS2X, which is an advanced version of the MHAPIS2 library. And the red line is the basic one, which is just purely doing point-to-point based solutions. And then the MHAPIS2XR has the green line, and you can see that almost the close to very flat curve we see on the left-hand side, as well on the right-hand side is like 1,000 nodes with 16 ppn, so 16,000 core MPI already used. There also we see very flat. And by the way, these designs are already available in our MHAPIS release, like MHAPIS 3.0. That is our new series. If you just download this, you should be able to even get the exactly same performance kind of things. Next slide, please. So then the question is like with a varying node count. So the earlier it was like for a fixed system size, we are trying to show the impact on the different message size. So here, if you see at the left-hand side, it is increasing the number of nodes. So this is where the SARP actually, or in-network computing capability, comes very handy. As you can see, the line is almost flat. So here we are trying to keep on increasing the number of the nodes. Let's say for 16 bytes, which is very common for HPC applications, the average latency almost remains the same, except after 2K to 7K, there the topology comes into the play. Because for the very large one, you are going through the upper layers of the switches, so there is more overhead there. And the right hand side also you can see very similar trend. And this was actually presented at the XIMPI conference. You can actually see more details there, but now the design is actually available for people to use. So this is all for small messages, but the bigger challenge is how do we handle the large messages MPI already use, and that too using the SAR. So here let me hand it over to Bharath, so he will go into more details.
Yeah, thanks, Dr. Panda. So the schemes that Dr. Panda presented kind of fall under the two-copy paradigm. So in a two-copy paradigm, you have processes writing to a shared memory region and remote processes reading from that shared memory region. So the reason it's called two-copy is because you have a copy in, which is a write to shared memory, and a copy out, which is a read from shared memory. So the schemes that implement reductions usually use leader-based algorithms. So what that means is you designate one process on every node to kind of take care of the internode operations as well as the reductions and the broadcast. So while this is really effective for small messages, it is not suitable for large message sizes. And there are like different reasons for that. The main reason is that you're kind of waiting on the reductions to complete before you initiate network operations. So that leads to suboptimal bandwidth utilization. And with an increase in message size, you're kind of always bandwidth bound, right? So that's the primary reason why these schemes will not work well. And the other thing is the two-copy paradigm also involves an explicit mem copy. So again, the time for mem copy also increases as you increase the message size. So on the other hand, there are single copy schemes which use transport such as XPMem. So with XPMem, you can allow a remote process to load and store to have load store access to your buffers. And this happens through an mmap or an address space mapping from a remote process to your local process. So this, of course, incurs overhead at initialization, but typically MPI libraries use some sort of cache to amortize this overhead. So now considering this and the fact that streaming aggregation is a switch level resource, which means that it has limitations and you need to address various bottlenecks. So this kind of motivates the need for using these single copy schemes and combining them with streaming aggregation to design an all-reduce collective. So now to realize the benefits or to see the kind of benefits we can expect with streaming aggregation, we kind of compared Sharp's LLT and streaming aggregation on 8 nodes. So LLT is also is an abbreviation for low latency tree. So it's the algorithm that Sharp uses for smaller messages. So as you can imagine, a tree-based algorithm is really good for small messages, but the problem is that you have multiple steps. So when you increase the message size, you're kind of bottlenecked, right? So that leads to suboptimal network utilization. So with streaming aggregation, Sharp does a ring-like algorithm which continuously, which uses the bandwidth of the network really well. And we see that on the right-hand side, where if you increase the message size, you're kind of seeing a pretty huge difference between the low latency tree and the streaming aggregation protocol. So one of the big bottlenecks in using streaming aggregation is memory registration. So which is very similar. So Sharp has its own memory registration API, just like InfiniBand. So with memory registration, you have expensive operations such as pinning the pages to memory. So and this is really expensive. So as I mentioned before, like with XPMem schemes, this kind of requires a cache that avoids expensive calls. So ideally, we want to do this once and forget about it. So the graph on the right-hand side kind of shows the registration overhead, like quantifies the registration overhead, and we see that it's like really significant the more you increase the message size. The second thing is that, yeah, switch resources are really limited because you're kind of using ASICs on the switch to do the reductions. And of course, not all processes can do this because you're kind of sending a lot of data from different processes. And also, you also need to place a limit on the number of jobs that can use switch resources. So as I mentioned before, this motivates need for our designs that kind of use registration caches to amortize overheads and also figure out a way to use sharp switch resources efficiently. So basically we analyze, to do this, we first analyze the impacts of chunking reductions. So this is to establish some sort of pipeline where we try to overlap the reduction operations with network operations and so on. And we propose an algorithm for large message order-reduce on CPUs that utilizes streaming aggregation and XPMEM. And we also show some evaluations against state-of-the-art MPI libraries. So to give an overview of our designs, we also use a leader-based scheme. So we designate one or two processes on every node as a node level leader. So the job of a leader in this case is to take a buffer and initiate network operations with sharp. So how we do that is we first chunk every process's buffer into PPN, which is the number of processes per node chunks. And all the processes are reduced to a single buffer belonging to the leader process. So for this, we use XPMEM for load store access. So it could be argued that you could do a direct mem copy to shared memory and then do the reduction. But the big advantage of XPMEM is that with direct load store accesses, you have a fine-grained pipeline established between the memory operations and the reduction, and that kind of gives benefits. So all processes will perform local reductions of a certain chunk, but only the leader process calls the sharp runtime. And the main motivation for this is to reduce the overheads of having many processes interacting with the sharp runtime, which is something that the runtime itself prevents, at least with the version that we ran our experiments with. So once the local reductions are complete, we want to overlap these with the non-blocking implementation of sharp or reduce. And we do this in batches to get good network utilization. So, and the final step is for the leader processes to broadcast within the node. So for our registration cache design, we use a standard AVL tree. And further data structure optimizations aren't really required because traditionally the number of buffers that are used with all reduce aren't huge. So an AVL tree just works really well. And so if a buffer entry already exists, just like any other cache, we directly get the registration information that the sharp runtime gives us, and then we return it back to the MPI library. So this leads to like around 5.6x reduction in the latency, and that's shown on the graph on the right side, where, as I mentioned before, you increase the message size and you'd see greater and greater benefits. So before going into the design, we also wanted to explain how we decided how to chunk the all reduce operations. So to do that, we performed a simple experiment, which is we took a large buffer and we divided it into multiple chunks, and we kind of measure the cost of one all reduce for that message size versus let's say when there are C chunks, you want to call C non-blocking all reduces and then await all. So the difference here is that we kind of want to measure the overlap at the network level. So we are trying to establish a minimum threshold above which the network does a perfect overlap. So we observed that with like 16K bytes, irrespective of the number of chunks, which is also the streaming aggregation threshold, we see the same latency. So what that means is a 1 megabyte all reduce is the same as issuing 32 16 kilobyte all reduces and then a wait all. But if you decrease the message size, then there is also some protocol switching that happens, and that leads to suboptimal performance. So using this, we can kind of have a baseline to start with, which is you need reductions of at least 16K bytes at the intranode level. But then we kind of tune this based on the network characteristics to make sure that we have a well-performing algorithm. So coming to our proposed all reduce design, we first cache all the buffer information. So there is like an init setup phase using shared memory, and this is really just small messages, so it's not very impactful to the performance. And then every process will, as I said, will reduce a chunk. So here you see P0 responsible for the red chunks, and then P1 responsible for the yellow chunks. And every process will then write this to a buffer, which is, let's say, located at P0 using XPMM load stores. And at the end of this step, you kind of have a reduced chunk that you can then do an all reduce with across the node. So then the leader process just initiates a non-blocking all reduce, and then you have all the processes starting these batch of reductions again. So yeah, so this is the reason we chunk this is the same as the motivation for pipelining, right? Which is you want to reduce the number of the amount of time you wait until the network is utilized. And we kind of see that 16 kilobytes is the bare minimum for us to start with. And we tune this for different sizes and system sizes and other parameters. So once the leader completes the reductions, it kind of performs a broadcast within the node. So this would kind of result in, this would end up with all the processes having the final reduced results. So coming to the results, we kind of, we run our experiments on two systems, one with an AMD processor and one with an Intel processor, and both have Mellanox Quantum 2 switches. And we compare against state-of-the-art MPI libraries, and we see up to 30 to 80% improvements over state-of-the-art, except for the 1 megabyte message size, where we kind of observed an increase in page faults. So that's something we need to investigate further. So the main reason for the benefits is that you're using shard for reductions, which leads to very low latency, and also increased parallelism within the node by having every single process participate in the reductions. So you'll see similar trends for 4 and 8 nodes, where you see 30 to 80% improvements on both the systems. Unfortunately, at the time of publication, we did not have access to a larger system with Sharp, but you should see an increase in the performance as you increase the scale. So, which is something you see here, where it was 30% for the smaller scales, but now it's gone up to like 50% for the larger scales. Another thing to note is that the page faults are less impactful at larger scales because the internode performance will dominate. Now I hand it over to Dr. Panda for the conclusion.
Yeah, so Bharath, thanks for explaining the design. So just to conclude this talk, as I motivated, so the overall idea is that how do we really optimize MPI all reduce, especially with the in-network designs available with the SARP. And we have shown here both for the short messages as well as for the large messages. One can optimize, and it can actually give you, in fact, performance benefits up to even 86%. The small message optimization is already available in our latest MAPage, and then the large message optimization will be available in a future release of the MAPage Plus. And ongoing work we are trying to do is to really try to see at an application level evaluation, the evaluation at the larger scale. And this is where, as Bharath was indicating, there are a lot of InfiniBand clusters, but not many of them have the SARF installed. So this is where we are seeing some problem. Once we have the SARF installed and available on the larger systems, then we'll be able to carry out these experiments. And the other thing which also is happening here, I mean, one is on the network side, another is within the node. And within the node, as we know, like we are increasing the number of cores. So this is where also we see a lot of new awareness comes into the initial phases. Like you remember the 5 phases we discussed, the first 2 phases and the last 2 phases. So there is also that interaction taking place on the overall performance, and we are taking a look at those. So with this, we will conclude the presentation here, and Bharath and I will be very happy to answer questions. Thank you. Next slide.
Cool. Thank you, DK and Bharath. Let's see here. We have a couple of questions. Can you discuss security issues such as you see evolving for switch memory allocation and management for multi-user systems?
Bob, thanks for that note. This we have not looked at it here. We are purely trying to do from a performance perspective. I think this is something the vendor who are providing this kind of a networking support, they need to at least provide some kind of a security issues. Okay, as long as that is there, then we'll be able to take advantage of it.
Cool. Also received a question, can the in-network computing concept be used by other interconnects and vendors?
Yes. I mean, this what we showed is, if you see, it is just a very like we just took the example of the SARP because that is already available on the Mellanox/NVIDIA InfiniBand switches. I know some of the other vendors are also working. The concept is very general, and it can be used by any other network vendors. I think as long as they follow the very similar things, because you need to allocate some kind of buffers, you need to allocate some kind of compute engines on the switches to perform these operations. So as long as you can handle both these things, any kind of network can be converted into like a in-network support.
Cool, thank you. Do we have further questions for DK and Bharath? Oh yes, okay, so we have one. Here we are. What is the minimum message supported in the Sharp SAT per reduction?
Bharath, do you have this answer?
Yeah, so that's a threshold that can be set on the system, but it would be 16 kilobytes as of now. So that's the default. But the sysadmins, or you can also, there are Sharp level variables that you can set to increase or decrease that. But in general, NVIDIA kind of recommends 16 kilobytes as the threshold.
Cool, good question.
So that was for the minimum, right? What is the maximum message?
So yeah, we've tried up to 128 megabytes, but I'm assuming it's as large as IB supports because internally they use IB calls, right? So I would say MPI will probably hit its limits first. So int max, I guess.
Yeah. Thanks.
Cool. Any more questions? This is good discussion. Okay, thank you guys. Appreciate it very much.
Thank you. Thanks, Bob.